All right. So welcome everybody to the community evaluation of Rubin survey strategies. Your chairs are myself, Lynn Jones, and Peter Yoakum. We are the LSST survey strategy team along with Eric Nielsen and Tiago Ribeiro, with plenty of direction from Željko Ivizic. And today I'm going to go very quickly through a recap of the pre-recorded material. So I hope all of you found that okay. We had videos on the agenda page, and we also had some additional information about those links on the community post referenced on the Slack channel. Basically, that additional information was just timestamps for the videos. So I'll just go through that very, very quickly, and then we'll hear from the different science collaborations. So first, as all of these sessions start, just a reminder about the code of conduct, which you all agreed to abide by at registration. And this session will abide by the Greek code of conduct. And also a reminder that all talks at this workshop are recorded, and you can keep your camera off if you prefer. Videos are posted shortly after this session. You can comment on Slack and ask questions on Slack or on the Zoom chat. And if you see questions on Slack, you can give a thumbs up if you say, this is actually a question that I'm also interested in. And as always, feel free to applaud at any time on the Slack channel. Okay, so like I said, we had a pre-recorded content with links and further details that was available on the survey strategy session post on community.lssc.org. There is the full link. If you haven't been to community.lssc.org yet, it's a really useful resource. It's a place where you can go and ask questions about for the whole community. It's open to the public, so you can get feedback, not just from people in the science collaboration, but you can also post questions for other people to see or discuss. The survey strategy is a section on community, and that's where I would prefer to keep the discussion about the survey strategy. It's nice because it's public, it's very transparent, and that's one of our goals for determining the survey strategy. So community.lssc.org, I urge you all to go check it out, ask questions there. It's pretty highly monitored by the LSST team. In particular, Peter and I and Eric will try to answer questions in the survey strategy section. So one of the things in the pre-recorded material was talking about the survey strategy process. So basically the path from here to recommendations from the SCOC, the Survey Cadence Optimization Committee, SCOC or SCOC. So the SCOC will take the information from our report, which we've just written. So I believe I have a link for the report in just a minute, but it's in the community post as well. So the UTIP will take information from the experiments that we've run so far and in our report and feedback from the community and talk to the community. And then at the end of this process, they will come back and give recommendations to the operations director on the survey strategy for the LSST. In the pre-recorded material, there's also information about the scheduler, both the background and changes in the scheduler if you've been already following along, and the basics of the LSSC survey strategy, just like what is the YFAST. We also have a video about the feature-based scheduler, that's our scheduler, 1.5 experiments, and the 1.6 potential schedulers. I'm going to talk extremely briefly about what those are. Basically, the FPS 1.5 experiments are a series of experiments where in each family we vary a single aspect of the survey strategy to look at the effect on metrics. So these boxes here are the various families that we have, and they're color-coded by families that deal with similar kinds of aspects of this survey strategy. There are 18 families, 105 simulations in this FPS 1.5 release. Then in the FPS 1.6 release, this is a much smaller set of simulations. It's 8 simulations, and they're called potential schedulers because basically what we did is we took aspects of the survey strategy that we experimented with separately in the 1.5 release and combined things that we thought might work well for particular science goals. So these sets of simulations are multiple survey strategy parameters are varying at the same time, but with one science goal. So these are more examples of how we might put those aspects of the survey strategy together. For experimenting and seeing like what is the effect of a rolling cadence, for example, you would do better to go to the 1.5 experiments and then look at this rolling footprint family. All right, so the next steps is we have this report on the survey strategy experiments, the 1.5 and 1.6 sets, and we've written that, passed it to the SCOC, and it is publicly available at PSTN-0151. So it's PSTN 51 is how we, in the project, we call this. And it's available on lssc.io. In this report, we noticed there are several places where metrics are missing. So photo Z is an important one. Transients and variables, where we're if they're very sensitive to the visit timing, this is an area where we might have missing metrics. Deep drilling specific metrics would be useful, and weak lensing systematic style metrics. And also, we did some experiments with mini surveys, so a Twilight NEO mini survey and a short exposure mini survey, and a DCR mini survey. And so metrics which are useful to look at the benefits of these mini surveys, the specific metrics would be desirable also. Some of these I know are in development in the community and just haven't made their way back into the metrics analysis framework math yet. So that's a loop we would like to close. The SCOC will be looking for feedback from the community about these simulations, especially in areas relating to the missing metrics. So they'll hold a public workshop in about November this year, and then have white papers. The call for white papers will come out shortly, primarily looking for things like metrics, perhaps also looking for comments on the survey, the simulations, if it doesn't align with the report that we have in March, approximately March next year. That would be when they're due. They will then work on creating initial survey strategy recommendation, and this will come with new simulation, maybe simulations, and hold a second workshop in fall of 2021, and then have finalized recommendations on the survey strategy December next year, and it will be fine-tuned throughout 2022. And as you've heard in other plenary sessions, the operations for the telescope won't start before early 2023. So those are our very swift recap of the status. Now I'm going to throw this over to the science collaborations for their thoughts on metrics or the simulations, or how their collaboration might be poised to go through these next steps. I have a list of people here. I don't know actually if that's how the slides turned up in order in this presentation. So we'll go to the next slide and we'll see who's up first.
Yeah, I think it is.
Okay. Great, Dan.
Great. Okay. Thanks, everyone. So this is going to be a presentation on behalf of the Dark Energy Science Collaboration, as well as the Strong Lens Science Collaboration. So we'll show some additional input from them. I also just want to thank Lynn, Peter, and the project team for being extremely responsive and transparent in this process. So the state of where we are right now, that we have finished a number of metrics for kind of what's called version 1.4, and Lynn, I think, just spoke about version 1.5, which we're not totally complete on. And DES basically has a number of working groups that cover a large variety of cosmological probes, so large-scale structure with lensing, 3x2, supernovae, strong lensing, kilonovae. And the challenge is in figuring out what all these different groups want. So we're currently working on a metrics paper that details all the metrics from the various probes. And I think we had in our head that the hard part was coming up with the metrics, and now we've realized that the really challenging part is to understand what our metrics mean and see if it kind of agrees with our intuition, and then trying to find some kind of consensus across multiple probes. And considering the challenge that we're finding this for DESC, I can only imagine how hard this is going to be across all the collaborations. Okay, now on the right, I show a plot that Michelle Lochner, who helps lead the observing strategy group with me, made. And maybe if we go to the next slide, I'm gonna show 3 versions of it and I'll explain it. Great. Okay, so this is how we are now visualizing different metrics from different probes of the various survey strategies that come in from the project. So I don't want to dive too deep in here, but I just want to have these as reference. So what you see in the legend is the metric, and then what you see on the y-axis is different observing strategies. So this is what kind of Lynn put in her different experiments. And then we show on the x-axis how much it improves compared to baseline, where baseline is the kind of the nominal strategy. And then Michelle made this for each probe, where we try to take the metrics and observing strategies that are kind of most sensitive to various changes, so we can understand what's going on. Now, if you look across these different ones, you could see some kind of general trends across different metrics with these different probes. But the tricky part gets into where things don't agree, or trying to evaluate, well, if it's a 10% improvement over baseline, is that worth us pushing on or not? And that's kind of the place where we are right now. Okay, so next slide. Okay, oh, I think maybe the top of this got cut off. Oh, interesting. Just 1 second. I'll just look at what I have. Okay.
It actually, yeah, sorry, this is probably a Chrome thing.
Okay, that's fine. I could just read off my version. So because I see the bottom half, that's totally fine. Okay, so what is the dark energy static science DHS? I'm just gonna quickly talk about static science and then transient science. So we need good photo Z's. We need deep galaxy samples. Then one thing that kind of we're really pushing for is low dust uncertainty. So basically EB minus V, extinction of Milky Way, less than 0.2, and then as large of an area as possible. So where we seem to have converged on for YFS deep kind of in the static sense is that about that currently 25% of the YFS deep survey area is not useful because of the high extinction mainly. And what we're proposing is to try to use about 70% of the YFS deep time at low extinction regions. So extend the baseline footprint north and south. This is good in terms of it's increasing the usable area, and then it is also increasing the amount of overlap we could have with spectroscopic surveys. And then the remaining time, what we prefer is for that to be for galactic science with the optimized cadence that those collaborations would want. And I'll just add that for the strong lensing science collaboration, they want to note that they really want good seeing in the blue end. Okay, so next slide. Great. So kind of same thing, but now switching to the transient side. So here we have kind of 3 main probes: supernovae, strong lens, and kilonovae. And there's certainly general trends that all of these different probes would like. I think what we're finding is that supernovae have extra requirements for it to be successful. I'm putting this here for reference. If you go to the next slide. Okay. Okay, I see the same thing happened. Okay, so what does the transient science need? So transient science, we want a large area and basically strong lens, QSO microlensing. This is from the SLSC, and kilonova, all like high area, and they would prefer not rolling. Our supernova group still prefers rolling, or that still seems to do better, but that seems to be kind of currently at odds with the other groups. The other big push is for a good cadence, so a large number of filter changes, and then season lengths of around 180 days to avoid edge effects. Now, the current baseline for the transient science is that there's still pretty large gaps between when we return to filter observation. So if you're observing a G-band, when is the next day you have a G-band observation, and that could be 13 days or more, which for a lot of transient science cases is still a bit less than ideal. And it felt like we were heading in the right direction, but then we've gotten this new weather model implemented. This is a lot of work led by Eric Nielsen. And what we see is that there'll be significant numbers, a number of downtimes where basically how long is the stretch of time where you're not observing. That's more than 10 days, and that's really hurting our transient science. So our supernova group has been working a lot with Peter on trying to push the filter cadence, and we've been looking still at this alt sketch philosophy, but it seems like it's just not buying us that much. And I think we know we want to get better, but it's unclear right now what's the path to do that. And we'd really like to work with other collaborations on this. Okay, so the next slide.
Okay, and you are a bit over time, so.
Okay. Oh, okay, and this now has disappeared. Okay, so I'll just say that left on the table. Okay, that looks good. Yeah, we're still working on the early reference survey. We definitely want the fifth field as the joint Euclid field in the south, and then for DDF, I'll just say that we're really interested in rolling deep fields where it could be synchronized with surveys, and we could get really high depth, higher than kind of the baseline plan. So I'll leave it there. Thank you.
Thanks, Dan. All right, so next up, we have Peregrine, and is Will, I'll let you guys take that away.
Yeah, Will's here too. All right, hi, this is Peregrine McGee once again. So we're still working on implementation of metrics and figures of merit for many of our science cases, leveraging off the 2018 Cadence white papers. We have lots of overlap with other collaborations, particularly transit variable sky, because we obviously a lot of galactic objects are variable stars. So things that are important to us, we work across the entire sky. But unlike some other collaborations, we actually need to work in crowded fields. So galactic plane, the bulge, magellanic clouds. So doing crowded field point source photometry and proper motions is important. So work is ongoing to calibrate the metric analysis based on experience, for example, from DECCAM. Dynamic range is an issue for us for a lot of stellar population studies in calibration. LST saturates at a fairly faint limit for us. So we would perhaps want to look at short exposures outside of the twilight time. We're looking at synergies for the external surveys. And also, there are some science cases where we would want to look at objects with extreme colors, for example, like young stellar objects, which are frequently seen under a lot of extinction, besides having non-stellar colors like very bright in the U band due to increasing signatures. So 0th order, more exposure is generally better. And okay, back, yeah, okay. Can you go back a few slides? Awesome, thank you. Right. So why time baseline is better? You know, we want to look at the coverage of parallaxes, and you know, what range of scene do we need to ask for in crowded regions? What's the distribution of epochs that maximize the science return? Okay, next slide. So there's, yeah, so our cadence requirements are have multiple aspects to them because we have a very diverse set of working groups, right? We're looking for everything from the solar neighborhood, you know, very low mass stars and brown dwarfs, local stellar populations. We want to look at star clusters, variable stars, so that puts us hand in hand with TVS, looking at variable at accurate photometry and astrometry in the bulge and in the plane. We want to look at galactic structure. We need to look at the interstellar medium. Of course, a lot of work with the magnetic clouds, and also we have a section on near field cosmology that puts us very closely into the desk-led dark matter project. So there's a lot of different things that stars midway and local volume has to deal with. And so we're in the process of working on those metrics. But then I think what's sort of unique for us is that we have to work in crowded fields. All right. That's what I have. Will, do you want to add anything?
Not really, just to echo Dan and thanking Lynn and Peter and the math team for being extremely responsive and transparent about the whole process and for answering all of our somewhat eccentric questions. So thank you.
Okay. Right.
Thank you, Peregrine and Will. All right, now we're actually on to the next slide. I think Meg is presenting for the solar system.
Hi, I'm Meg Schwam. I'm co-chair of the Solar System Science Collaboration. So I want to say that in terms of our preparations, one thing that has been decided is we have a science roadmap. It was one of the things that I finished when I became co-chair 3 years ago, is to make sure we have the argument between what are our primary science goals, so that now we don't have to argue about that. We have to just go down the list. So our primary metrics are in reasonable shape in the sense that detections drive everything. That basically everyone wanted large number of objects in all the different solar system groupings. So that means light curves and colors are great, but they're second order to detections. And so it means that we at least in bulk scale know, and broad strokes know how to start looking at these simulations, because the first thing we're going to look at is number of detections in different solar system populations, and then go down into the other metrics. So that also means that we have a lot of those basic things are in math. Those were all pretty much coded by Lynn and Peter and their team. So thank you for all of doing that work. I would say that we might want to add some of the more orbital populations that are not currently represented in the math metrics that are online on community that you can look at, or in Lynn's reports. Those are not going to really change the answer. They might emphasize where things that already look bad make them look even worse. But I think even with what we have, we can probably start making some decisions there. And maybe we can go to the next slide. Okay, so the reason why I have a stoplight up is because I think that's basically how we need to evaluate the simulations for the Solar System Science Collaboration. I also want to say the reason why I think it's good to go in this way is kind of to say where we like these are getting us in trouble and with what populations, and then these are the ones that absolutely no. And distinguishing where, where we can evenly distribute the unhappiness is sort of in between, between that green and that yellow, right? So can you lose 1% of your NEOs and your asteroids to get you know, a significant gain in outer solar system populations, we're probably going to make that trade. But again, we want to try to make sure that we're able to do the science that we prioritized in our science roadmap. And can we go to the next slide? So I really do think that that stoplight analogy is going to be the best way for us to sort of go through these simulations. This is an example, and one thing I want to say is that our science collaboration really didn't make these. Lynn made these plots, and I think one of the things that we're finding is it's very hard to get over the barrier. There's a lot of information to take in, and I think the intro talks in this session are fantastic in helping get people in the door, because we did write a lot of these white papers several years ago, and there's now new people in science collaboration that weren't around then, or were in graduate school then, and now we want to make sure they can contribute too. So having plots like this already made by Rubin helps, because this is much easier to digest, and then you can start thinking about where the tensions are, versus if we all have to go and figure out how to pull out this information. So I want to say big thank you to Lynn for bringing these kind of plots onto communities, so that it helps us get more of our science collaboration able to participate in these discussions. So this example is from pulling from community, one of these plots, and this one's looking at footprint. So all the different colors are different solar system populations. The dashed is just a fainter, basically in absolute magnitude, so smaller object in the population versus a brighter one. And if you hit next, Lynn, I think something should pop up. There we go. So in terms of that, you know, analogy of stoplights, I'm just looking at the ends and the extremes, but you can see that, you know, on the left, right, you see that the Kuiper belt objects, the TNOs, drop off significantly, and that's one that doesn't have the northern ecliptic spur in it. So that's when we immediately say, red light, don't do that. That's not something that we think is going to help us do our science. It's probably against everything in terms of our science priorities, and significantly getting science because it significantly impacts outer solar system science by a lot. That line's actually way off the plot, and this has been condensed. And you might say on the right, actually this new baseline, that's our one of the end state, that footprint seems to do pretty well. We get a very significant increase in the number of Kuiper belt objects and trans-Neptunian objects, and take a little bit of a hit in the other populations. And so that gain seems to be probably worth it. And so I think is for us, this is how we're going to go through these simulations, is sort of green light them, yellow light them, and red light them with these explanations for why we think these things are better. I think the one thing we just need to figure out is how do we get all this information in a way that we get, especially early career people that work on this data set, as well as other people in the science collaboration, able to easily digest it. And I think having these plots and the SCOC workshop in November is going to be a great place for us to be able to make these sort of traffic light analogies. And that's all I got.
All right. Excuse me. Thank you, Meg. I'll just add really quickly, sorry. This plot, actually, I put it up on community, but it is also, it's part of that report that we've created for the SCOC. So you will see the same kind of plot with the same background shading, for example, for the other groups of metrics that we currently know about and are running in math. So next up we have Billy Gordon is presenting for the AGNs.
Hi, yeah, so I'll summarize the activities from the AGN Science Collaboration in terms of metrics. First thing I want to do is start by advertising the work that Weizhang Yu, grad student Drexel, has done to enable OBSIM analysis within the SciServer environment that's been set up at Johns Hopkins University. That's with the 1.4, 1.5, and 1.6 simulations. So there's instructions at the GitHub link there, and there's a 36-minute video that basically shows you how to get set up. So that's the platform that was demonstrated during the hackathon last week. And there's actually a new example of multi-core processing at that notebook link there that allows you to run up to 16 cores with 260 gigabytes of memory. So that may be useful for some groups that don't have access to other powerful computers. So the activities are all sort of, of course, in the context of the roadmap. So if you go to the next slide. We had 3 metrics based on white papers that we are primarily working on. As Fed mentioned this morning, I think, and this is certainly true with all the science collaborations, the biggest barrier to having more mature metrics and more metrics is just funding. You know, basically we're sort of doing the best that we can with what we've got. Discussions are being held on that Slack channel that is indicated there. The first metric that I want to review is one that's being worked on by King-Ling Ni, a grad student at Penn State. Basically looking to compare how the actual depth is of the AGN proposed DDF is to the proposed depth, right? So you can see the bars on the bottom are indicating the proposed depth, and obviously the histogram is indicating the depth that we're actually getting. And so you can see it's pretty good, but you know, maybe not as good as we might like, and so we need to do some more work to analyze that. Go to the next slide. So one of the things that we're interested in AGNs is differential chromatic refraction, because it's very powerful, both for identifying AGNs, actually anything with a spectral break or a strong emission line or a strong absorption line, and also for photo Z. So there's a new metric that's based on a metric that Peter has written that's generic for all science cases, basically just looking at how well we can measure the slope of the DCR, basically how well we can measure the DCR, and that's indicated by the plot on the left, showing 19 different families at a particular magnitude, and the notebook there can go through all 100 or odd families and different magnitudes. And then the plot on the right is the thing that is actually AGN specific, where we basically say, okay, what's the expected slope for a quasar at redshift 1.6, 2.6, and so on. And so what's the signal to noise at which we're measuring that slope? And obviously, if we get signal to noise 10 on a slope at redshift 1.6, that provides a very strong prior to the photo Z, if not, uniquely identifying it as a redshift 1.6 quasar. But if the signal to noise is 0, then the DCR isn't gonna help. And again, we can do that as a function of magnitude and family. And then the last slide. So we're also working on a metric, also developed on an existing metric. So we're basically looking at the distribution of pairs of observations, but what we're interested in is log space. So we want to look to know how many times we sample at both 30 seconds and 10 years, and that is going to tell us something about how well we constrain the power spectral density or the structure function across many timescales. So particular interest there is in analyzing the effects of rolling cadences. Roughly speaking, I would say AGNs benefit from a mild rolling cadence, but extreme rolling cadence is bad for us. But that's something that we're still working on. So like it says, a lot of the code has been developed. Obviously, we can make plots like that, and we just need to turn it into some actual metric scaled to 1 so that you can put it on a radar plot and actually make some sense out of it by just staring at the plot. And I think that's it.
Okay, Harry Ferguson from Galaxies. So we have a subgroup focused on survey strategy, although I would say that most of the people who have contributed have done so wearing either project hats or desk hats. And a lot of our collaborations needs are represented quite well by the desk static science needs. So there's not a whole lot that's unique to what the Galaxies collaboration would focus on. But I'll mention a few things that probably don't have, well, certainly don't have specific metrics in math at the moment. So I think we would tend to favor longer exposures over shorter ones because being more sky limited is a good thing, and we don't have variable sources. And so, for example, the 60-second possibility for the U-band is quite interesting. U-band depth is important at redshifts between about 2.5 and 4, say. Probably that's not, that doesn't come out of a very simplistic photo Z metric. There are some studies that have been done looking at photo Z's as a function of redshift that show that U-band's quite important there. The Y-band's useful for a few science goals. One of them is red sequence cluster finding at high redshift, maybe a little more specific than the U-band over the whole wide survey area. I think the collaboration would favor completing one deep drilling field early in the survey. 10 field could, in some sense, influence a lot of the strategy further on and get out earlier science. And rolling cadences are probably generally favored, partly also by the desire to get deeper faster over smaller areas is probably gets out more of the galaxy science sooner. Looking at the SCOC report, the DM's heavy survey strategies look quite helpful. I'll show on the next slide. We're starting to think about seeing and how much we might care about that. Now, our objects are by and large things that are resolved. They're not point sources almost by definition. On the other hand, the deblending is something we're quite concerned with, and the first step in that is finding peaks. And that is heavily affected by seeing. Also, the photo Z's are going to require good U-band calibration, and some of the DM strategies looked at that. I think there wasn't a DM heavy strategy that looked at avoidance of ghosts, or what Robert Lupton calls ghoulies, scattered light from sort of random pieces of equipment. Ultimately, it'd be nice to avoid those if you get to the point of being able to predict them and maybe adjust rotator angles and things like that to avoid them. The next slide just looks at seeing a little bit. So the finding of peaks is strongly influenced, and the simulation on the right shows essentially one exposure in the first quartile of seeing, so 0.44 arc seconds. And then on the right is 10 exposures co-added, all with 0.81. So that's the 75th percentile of seeing. And there's just been a standard DAO photo Starfinder run on that. And you can see that even the one exposure, 1/10 the exposure time, identifies a lot more separate sources, which you can then go back and deblend and do force photometry on and so on. So one possibility to think about is just ensuring that you get uniform, a few samples at good seeing in every field. That was one of the tests that was tried. But you could also think about whether to put that in one band preferentially, and maybe to even do further, make sure that the 10% of the observations have the best 20% of seeing or something in the I band, for example, where you might be most sensitive to clumps and variances. But we haven't really looked at that and quantified that to the extent that you could actually use it yet. The last slide just shows ways we could contribute in future, hopefully in collaboration with other science collaborations in the project. So defining metrics with the deep drilling field, we'd definitely be interested in contributing to. Refining the photo Z metrics and helping to refine the DM heavy metrics would be things where we think we could contribute.
All right, thanks, Harry. I'll just say the good seeing family is, I would be very interested in seeing what metrics you can come up with that will help us distinguish between those, because we do in that family look at, like, what if we just try to have good seeing in I band or G plus I and various band passes like that. So that'll be really interesting. And now we have Rachel Street and Fed are going to talk about the TVS And the metrics hackathon, I'm not sure how they've split it up. So
neither were we until very recently. So I'm going to kick off, and Fed will talk about the hackathon in a few slides' time. So just to summarize what TVS are particularly interested, the nutshell, it is all of the things. We have in the white papers that we wrote a couple of years ago, TVS proposed 20 metrics which cover everything from the time series and the cadence to the footprint to the information content, image quality, population, and even alert detectability in terms of cadence distributions. We wrote code for 17 of these metrics. That software is at various levels of integration with the math framework. There are an additional 3 metrics which require some new software development at this stage. But the area that we really want to focus on, I think, is going to be the development of the red light system that Meg mentioned earlier, actually evaluating how we judge whether a simulation is better or worse for our particular science cases, and the thresholds and the condition boundaries under which they're applied. Next slide, please. I want to point out particularly that we had a group dedicated to identifying truly new parameter space, so identifying true novelties in the data. This was an area that really wasn't well explored at the time, and the group have done a tremendous amount of work and even have a paper in progress that compared a number of different simulations in the different families, as you can see in the plots on the right. They've developed a number of comparison and display tools, such as this plotting code, so that's been really helpful for and available to other people. They've got metrics for the color, magnitude, time evolution, and motion, and I believe there's work outstanding on the morphology and association. Next slide. Federica said she was having trouble with a storm. Fed, are you available?
No, I'm here. Sorry, I was.
You were here. Okay.
I was typing on the chat that we're going to punt on morphology and association under the premise that morphology is less sensitive to cadence, or at least as far as I understand it, and association comes from having measured well the other parameters that we had discussed. So they're not in progress. They just will not. It will not. The map will not be extended to those. Right. So this is not just a TVS effort, but led by myself and Rachel, so led by TVS, with the participation of most of the other science collaborations as represented by the chairs. In fact, I think all of them, as well as the Rubin Upsyn team and the Rubin community engagement team. We had Peter and Melissa on the proposal. We asked for funds to help us support a metric hackathon before this PCW. And we got the support from the corporation through the Enabling Science grant. And we organized a hackathon for all Rubin science collaboration members, but really for the entire Rubin community, to talk about where we are with the metrics hackathon as a whole among the science collaborations. So we ran this last week, Thursday and Friday. We had 50 participants. We had to cap the number of participants because we weren't sure we could effectively support the work and coordinate the work of more than 50 participants. But we filled up all the spots. We had representation from all the science collaborations. And also I want to emphasize that a lot of what we were planning to do was to present the participants with the possibility of running maps on the SciServe environment. SciServe environment is a cloud environment that is ostensibly very similar to what some aspects of the Rubin platform, Rubin computational platform will be. And TVS cannot take credit for that because that was really entirely set up and organized by Gordon Richards and Wei Zhong Yu from the AGN Science collaboration. So they enable the LSST stack and math by installing them on the SciServe, and they uploaded all the metrics. So now anybody that wants to run all the options, so anybody that wants to run maths can do that without having to install the LSST stack or the relevant math software. This is huge, I think, because in the time since the math was written, I've worked a lot within TVS on trying to make sure that people would embrace it, because I think it's a great software and would be able to use it. But there were a lot of hurdles on the way, both, you know, computational power of the laptop that you would run it in, different platforms. It was just very hard to get the full installation running. We moved to containers. That solved some of the problems a couple of years back, but we still couldn't get the whole community to sort of embrace and participate in the process. So I hope that this smooths some of the technical hurdles. In the metric hackathon, we asked people to tell us what metrics they had over the course of the history of the science optimization scheme, what they had written. And we collected information about 39 metrics. So we're able to identify some metrics that were effectively just duplicates of others, and we have a documentation. We have a set of slides that can serve as documentation to understand what metrics have been written by the community, how we can consolidate them, and how we can organize support for the community to finalize the ones that need to be finalized. They are at all stages, like the TVS metrics, they are at all stages of development. Some are just conceptualized, but no code has been written. Some of them have code written. Some of them, that code has been written by the authors of the metric, but still needs to be integrated in the math. So it needs to be validated for functioning properly in the math and Opsim environment. And conversely, some of them that have been conceptualized, but for which no code has been written, need to be validated by the scientists that had conceived them, to see that the way in which they were coded up by, heroically really, by the team of Chu, Peter, and Lynn, is done in a way that actually does deliver what the science scope intended, for which obviously you need a domain scientist, and we cannot ask Peter and Lynn to master all of the domain so that they are able to do this all by themselves. So the idea of this was to figure out where we are and figure out how to support the community moving forward, including coordination with the Rubin team. We split the 50 participants into breakouts. We had a number of tutorials. The tutorials are available online as videos, including like step-by-step, how do you log on to SciServe, how do you run a simple metric, how do you aggregate metrics into results that allow you to compare them, and visualizations that allow you to compare them. But then we split into breakout rooms, and just briefly, next slide. Sorry, I was trying to change the slide, I couldn't. And briefly, I'm going to mention 6 breakout rooms. There was a sort of transients and variable breakout room. This included people both that work on mostly TVS, but also will be relevant for desk and for the variability cases of the other science collaborations. It did cover a discussion that included both galactic variables and extragalactic transients and galactic transients. So by that, the difference I mean, galactic variables are the kind of variables that probably will benefit from periodicity assessment. Typically, you don't have that in transients, and typically variable phenomena in the extragalactic sky are transient, but there are also transients in the galactic sky. Generally, we also know that we can coordinate with DESC. DESC has kindly offered support to help us use the Monte Carlo infrastructure that they are using for transients like supernova type 1a, so that it can be extended to other transients. So that's a route that can be pursued for a lot of those metrics, to just drop your transients into the Opsin and see what the Opsin returns. It's not as simple as that, but we can leave it at that. The microlensing team has been very active for a long time on metrics. They're focusing now on bundling up their metrics for different science cases, and microlensing includes stellar and black hole lensing, and identifying and catching events as they're happening and quasar microlenses. So it's a quite diverse although specific science field. And they are one of the teams that had done the most work early on. So I think they're at the stage where they need to consolidate their work and document it properly. I'm going to skip over the DCR because Gordon has described it earlier and showed this plot, but there was a DCR breakout session. Next slide. There was a PhotoZ session. My understanding is that PhotoZ doesn't have to, the investigation of PhotoZ doesn't really have to create metrics. They can simply rely on very high level statistics about the field, such as the signal to noise ratio per image per filter. So they're trying to aggregate the result of the existing metrics into what in some cases has been called the figure of merit. In other cases, I'm not sure what, I'm not sure if we're moving away from the concept of figure of merit, but so they're not at the stage where they need to code. The crowded field, people with interest in crowded fields are doing a lot of work on metrics, both in TDS and in seismic developable volume. One thing that I want to highlight is that they have found that the existing crowded metrics that are being run automatically on the opsims tend to be pessimistic, which I hope is good news. And then we had the discussion, what we called boundary condition, in a somewhat cryptic term. But what we meant is, what is the best way with which people can, once they have a metric that returns a number for their science, how they can put it together and give helpful information to the team. Is it ranking or grading? Can we triage some metrics? How do we allow you to triage some opsims effectively? And then.
Thanks, Fed. And thank you to everybody presenting for your science collaboration. I think that's the last, oh, sorry, you had one more slide, but.
No, those are just
courses.
for
Okay.
people to click on.
Okay, great. I will make sure that these slides get back to the channel, because people were contributing up to the point, and I didn't put this up super early. I don't think this is on the agenda yet, but I'll make sure that it all gets back to the agenda page and onto community. So now we have a little bit of time, 8 minutes for questions. I think Peter has been tracking questions as they come through, and maybe can direct us on there. What I hear is that there's a common theme of like, okay, metrics might be hard to make, but even once you make the metrics, how do you still evaluate the runs? Which I think is great, and that's what I was really hoping you guys would share some ideas on how you're approaching that. So, perfect.
Okay, so looking at the chat, there's been lots of good chatting going on. In the chats, there were some more votes for deeper U-band coverage, and so different people were inspired by Harry saying like, yes, we like deeper U-band images as well. And so I'll just throw out that you know, there are also transient groups that want more U-band images. So if you think deeper U-band is good for you, you should definitely try to quantify that and pass that on to us so that we can, the SCOC can take that into account, because they're definitely, that's one of the tensions we've identified, is more U-band images versus fewer deeper U-band images. And the other question that came up was, what about the satellite mega constellations like Starlink? Do we have a metric for doing that? Should we shorten the exposure time? And I'll go ahead and take that one. Yes, we have been worried about the mega constellations. Tony Tyson led a paper recently that's now in the archive where we looked in depth at how Starlink could impact Rubin observations. And basically what we found is at twilight, many of the mega constellations would be illuminated, and many images would get streaks in them, basically to the point where we can't dodge them. There's no efficient way to find find sucker holes in the sky to do things. We would spend so much time slewing that the telescope would become incredibly inefficient. And one of the nice things that we found doing observations of the satellites that are going up now with DES is that we do not think the Starlink satellites would saturate images, which is nice. They are slightly out of focus, so the streaks are a little bigger than a PSF, but there are still lots of usable pixels even if a streak goes through. So as the person who would have to dodge the satellites, I am advocating for minimize them, not dodge them completely, because dodging them completely, the cure is worse than the disease. And we'd lose a lot of pixels that way. So we're currently looking at that. The big tension is that, solar system folks would like to look at high air mass at twilight to get solar system objects interior to the Earth's orbit. And that's where the most illuminated Starlink objects are. So really that's the main tension right now, is can we still do interior to the Earth solar system objects in a mega constellation contaminated regime? And that's kind of an open question.
Yeah, and I will add one thing, that the dodging was a fairly simple dodging, and I don't know if it will end up being different if you know ahead of time, like before you even go to the field, that there might be a satellite in that location. So that would depend on a different kind of cooperation with the megasat people to tell us exactly where their satellites are. I don't know if it helps. The problem is, because we have so many slews, if you have even like 1 or 2 seconds addition to your slew time or waiting, then it's a huge impact.
Looked like Federica had a hand up, maybe?
Yeah, so just to say that, there was recently a meeting about this, and I want to emphasize that, we talk about SatCon and the Tesla sats, but there will be a ton of company and organizations that will do this. And so the idea of coordinating with them in itself might be untractable, because they will have hordes of satellites that are launched by different companies and with different degrees of interest in collaborating with us. And that once you do that, if you're thinking about the transient science, then you still have to deal with, like, are the images that I'm taking gonna enable follow-up in a reasonable time scale? Or is that field gonna that is available now for observing without satellite gonna get rained on with satellite in time scales that I'm interested in for follow-up, which I don't think is something that the Rubin scheduler could digest.
That would be pretty hard. Yeah. Wouldn't it be nice if there was a global regulation agency to make them all register their satellites and keep track of where they are and things like that?
And that's why I teach in a public policy school, because science is important in public policy.
Okay, any other questions?
So were there questions on Slack? I don't have Slack up, so.
Not much. I think there was some discussion about MIG's stoplights, but it didn't really. I think it can stay on Slack.
Okay, all right. Yeah. So in that case, we have sort of only about 3 minutes left. If anybody else had some comments on, like, things that we might be missing in sort of our tutorial information as well, that'd be great. I see Fed is a hand up.
Along those lines, I want to encourage people to continue to reach out to us who organize the Metric Hackathon, and we want to continue to support this work until the strategy is finalized. So if you have missed the hackathon but still would like to enjoy the support that hackathon enabled, definitely that's a possibility.
Yeah, I thought it was really great that the Psi server was set up, and I recognize that that's an issue. I will say I know Peter also set up a notebook somewhere where you could do the work to develop a metric completely outside of any of the LSST software framework. So that might be another resource that we should make sure we put up on community that people can see. Once you have a metric that you are happy with and they're working, we can run it within math. And this, one of the things that I think it was Gordon mentioned, in terms of like comparing all the simulations, there's lots of information, right? This is a very information-rich environment. To compare a lot of simulations, it's useful to boil all of that information down to sort of a single number or single number per metric, so that that histogram of the time distribution maybe becomes just one number. And then, so for the metrics that we already have, those single numbers are available in CSV files that we've put up online, and we'll make sure that it's mentioned in some of the community posts, but we'll make sure that that's maybe a bit more prominent there. All right. So thank you, everybody. We can finish up 1 minute early and enjoy the break. Thank you all.